Okay, I guess we'll get started then. So today we're going to discuss basics of quantum entropy. And next time we're going to discuss what are called generalized measurements and so-called quantum channels. So what I'll explain on all these topics is in my lecture notes, which are called a mini introduction. If you look on Google for me and the mini introduction, you'll certainly find this. I also recommend Preskel's chapter 10. Which is, the title is something like Quantum Shannon Theory. So, the basic setup is that we consider a so-called bipartite system. That just means a system with two parts. So the two parts have Hilbert spaces HA and HB, which for today are usually going to be finite dimensional. You could think of a spin system, or you could think of a molecule where we're only interested in finitely many energy levels, or you could think of a finite dimensional approximation to anything. And then the combined Hilbert space is a tensor product, HAB equals HA tensor HB. Now, a state psi AB in HAB could be a simple tensor product. Of states of the two systems. Now, if so, and you're measuring the A system, you can just forget the B system and just describe the A system with the wave function psi A. So, well, why is that true? Well, measuring the A system means that we have an operator that's something on system A tensored with the identity on system B. And measuring it means taking its excitation value. So we want to measure psi AB. Well, we want to calculate what we measure, which is the excitation value in the state psi AB of the operator OA tensor 1 on B. But by hypothesis, this is just psi A tensor psi B so it will factorize. And the part that involves the B system is 1 if psi B is a unit vector. And so our answer will just be what we would have gotten by measuring OA in the state psi A if the B system hadn't existed. However, of course, the case that the vector is a simple tensor product is highly atypical. A typical state is not at all a tensor product. If, let's say, if the A system has a basis of states IA and the B system has a basis of states JB, a generic state is a sum over I and J. Well, I'll just write as a sum over I and J. They run over their appropriate ranges of coefficients alpha ij times state I of system A and state J of system B. So the state can be represented by a matrix, W, let's say, the matrix whose matrix elements are alpha ij. It's a general m by n matrix. So the previous case was that W was of rank 1, but in general, it's a completely general m by n matrix. However, we can do the analog of diagonalizing a matrix. So we can transform by a unitary operator on HA and another unitary operator on HB. That'll transform W, I think we'll go to UWV transpose. And then there's a canonical form of an m by n matrix up to this operation, which is diagonal, except that there might be a different number of rows and columns. So in the case that there are more columns than rows, the diagonal form looks like that. If there are more rows than columns, it's the other way around. So up to a unitary transformation on the two sides, we can always put any state in this form. Yes?
We know there is a singular value decomposition that such that U only acts on HA and V only acts on HB.
I didn't make a singular value decomposition. For an observer who's studying system A, the group of symmetries of quantum mechanics are unitary operators on system A. For an observer studying system B, the natural symmetries of quantum mechanics are unitary operators on system B. So I let the A observer make a symmetry and the B observer make a symmetry. That acts on this matrix W by W going to UWV transpose. So now I asked what was the canonical form of such a W under that operation. And the canonical form is to diagonalize it. And you can even assume that the diagonal elements are positive. So, you see, once you put it in this form just by letting U be a diagonal matrix, you can rotate the phases of the diagonal elements and make them all positive. So in fact, the canonical form, I could write it more explicitly with positive matrix elements that I'll call square root of P1, square root of P2, up to square root of Pm. And then there are extra rows and columns of zeros. For definiteness, I'm writing it as if there are extra columns of zeros. So that tells us that any psi AB can be put in the form Well, m is the smaller of the original m and n of the square root of pi times the state I of system A tensored with the state I of system B. This is called the Schmidt decomposition. So, with that decomposition, you'll see that the norm of the state is the sum of the pi. So, to get the state to be a unit vector, we want the sum of the pi to be 1. And that means that we can interpret the pi as probabilities. Well, what are they probabilities for? So let's again make a measurement on system A. That means we'll take the excitation value in the state psi AB of some OA tensor 1. Well, what will that be now? We have to write the formula for psi twice, once for the broad, once for the ket. So 1 will give a sum over the square root of pi, 1 will be the sum over the square root of pj. Then in the ket, I'll get I of system A times I of system B. Then the operator is OA tensor 1 in system B. And then over here I'll have J of system A times J of system B. Sorry. When I made this Schmidt decomposition, I should have emphasized that the canonical form has the property that IA and also IB are orthonormal. We can normalize them to be unit vectors by possibly changing p. So when we made this decomposition, we could simply normalize IA and IB to be unit vectors until we say that p was not well defined. So I made a mistake in skipping that step. Since we should have specified that they're unit vectors, we can now take the inner product for the B states, and that's going to give us a delta Rj. So we do the sum over the B states, and we're left with the sum over I of I, OA, I. So an observer only making measurements of the A system can describe the situation by saying that the A system is in state I with probability Pi. The A system is in state IA with probability Pi. Now, any questions on that before I go on? Now there's another way to write this which is useful. We simply take the bra and move it from the left over to the right. So we write this as the trace of OA times the matrix II. The matrix II is the projection operator onto the state I. The orthogonal, Hermitian orthogonal projection operator onto the state I. And this, in turn, we can write as the trace of OA times what I'll call rho A. Rho A, which is the sum of PI times is called the density matrix for system A. And it summarizes everything you need to know about the state of system A. Because if you want to make any measurement of system A, the expectation value of the outcome is just given by the trace of your operator times the density matrix. And everything you might do in quantum mechanics ultimately comes down to measuring an expectation value of something. We could apply the same logic and we'd find that the density matrix of system B has the same form but with the B states. And that would be the density matrix for system B. So if a system, okay. So a definition is that a density matrix rho on a Hilbert space H is a positive Hermitian operator whose trace is 1. You can see that rho A and rho B have that property because the trace of rho A and also the trace of rho B is the sum over I of PI. And as we explained before, assuming we started with the unit vector, the sum of the PI's is 1. So what we've arrived at here are density matrices. And conversely, any density matrix could arise in this construction. Because if rho is any density matrix, let's say on the Hilbert space HA, we can diagonalize it when we diagonalize it, we get something that looks like this. The PI are positive, since rho is by definition positive, being a density matrix. Positive means positive semi-definite. So some of the rho might have 0 eigenvalues, but it doesn't have negative eigenvalues. But there are no zeros in this formula because if p were 0, we would just omit one term from the sum. So when we write such a formula, we always assume that the p's that we write are positive. So any density matrix can be diagonalized by a unitary transformation on HA and put in this form. And then you see that, well, let me specify that these are states of system A. Then we see that rho is the density matrix of a state. for example, we can take the state to be what it was in this derivation. Here, the states IB live in any Hilbert space HB that's big enough. So the number of terms in the sum is equal to the number of eigenvalues of rho. So as long as B has a Hilbert space that's big enough that it has that many orthonormal vectors, then we can pick orthonormal vectors in the B Hilbert space and write this state. And its density matrix will be rho. So what we've learned is that every density matrix has a purification. So every density matrix on a Hilbert space HA has a purification in, it's usually called purification on HA tensor HB for any HB that's big enough. Now, the purification is, of course, not unique, even if you decide which HB you want to use. Because even if you pick HB, you still have to pick these vectors I sub B. But you can see that the purification on HB is unique up to a unitary transformation on HB. Because if we were given any other set of orthonormal vectors, I tilde B, let's say, there would be some unitary operator, I'll call it UB, a unitary on system B, that maps IB to I tilde B. And therefore, it would convert this psi AB to a different one. So the purification of a density matrix isn't unique, but it's unique up to a unitary transformation of the purifying space, HB. And it's essentially unique. And if you're only measuring the A system, you don't really care what the B system was anyway, so although we had to choose it to pick a purification, it didn't matter. So if you're studying a quantum system in the lab, for example an atom, and you haven't specially prepared it, it's wrong to assume it starts life with a wave function. It started life with the density matrix. Depending on your point of view about quantum mechanics, you might believe that the whole universe has a pure state wave function. I don't know whether that's a correct point of view or not. But even if it is a correct point of view, a subsystem, such as an atom you study in your lab or the Milky Way galaxy, or really any subsystem of the whole universe, if it wasn't specially prepared to be in a pure state, it isn't. Because, as we've seen in this discussion, a pure state of the whole world corresponds to a density matrix of a subsystem. So the normal state of affairs of any quantum system is to be described by a density matrix, not by a pure state wave function.
HB being big enough, does this mean that the dimensions must be bigger?
Well, given rho, given this formula, we wanted to define this, or this version, let's say, with the i's. The IBs are orthonormal vectors in system B. And the number of them has to be, the number of them we need is the number of terms in this sum. Yes, right. HB could be bigger, but then we'd waste the extra space. Then that would be the case with a lot of extra columns of zeros in my previous explanation. Any other questions?
Does it make sense to take just another copy of HA or not?
We could, yes. So HA itself is big enough because the size of HA is at least as big as the number of terms in the series, in the sum.
Also, do you care about like the ordering of P1 through Pn or no? Like P1 is greater than equal to P2?
We could choose to order them, but for nothing that I've said has it been importance. Any other questions? So, okay, the generic state of of something you might be studying in your lab will be to be described by a density matrix. And there's no way to learn any more about how it was prepared except by trying to determine its density matrix by measurements or other manipulations. So, for example, well, how, if I was preparing, suppose I wanted to prepare something in a particular density matrix. One way I could do that is to prepare the state I with probability pi. So if I want the pi's to be, suppose there are only two states and I want probability half. I flip a coin, and if it's heads, then I give you state 1. But if I get tails, I give you state 2. So that's an example of preparing this state with probabilities a half. The state we'd get that way would be a half times 1, 1, times the state of my coin where the coin was heads. And then there's a half times 2, 2, the state with the tails. Now, when you study the system, which is in state 1 or 2, all you're going to be able to learn is that it's in this density matrix. You won't have any way to decide that I prepared it by flipping a coin and preparing state 1 or state 2 with probabilities 1/2 each. In fact, that may not have been the case, because this matrix is actually a multiple of the identity. Since we took the probabilities equal, that matrix is just a half of the identity. So it's a half of 1 prime, 1 prime, plus 2 prime, 2 prime, for some 1 prime and 2 prime, other orthogonal states, orthonormal states. So it might be that what I really did was to flip a coin and prepare 1 prime or 2 prime, depending on whether my coin came up heads or tails. So there's no way you can distinguish this one from this one by any measurement, because they simply correspond to the same matrix. So once you get a quantum state, all you can learn about it is to probe its density matrix by whatever manipulations are allowed by quantum mechanics. And we'll discuss on Thursday in general what manipulations of a density matrix are allowed by quantum mechanics. Its prior history about how it was prepared and how it might be related to the rest of the universe is lost. All you can learn about is the density matrix. Let me give an example where that's an asset. Suppose you're studying an atom. You're shining it with photons. It interacts with the photons. It might become excited. It might scatter a photon. It might become excited, and then later it goes back down to a lower energy state, emitting another photon. If you tried using a pure state, you'd have to keep track of all the photons that go by. And so the mathematical formalism you need would grow without limit as your atom interacts with more and more photons. So it's a big relief to get rid of all that and instead describe the atom by a density matrix. if you describe the situation by a density matrix, then no matter how much happens and no matter what the atom interacts with, the mathematical formalism you need doesn't get bigger. But there's a question we might ask. What if the combined system AB already was described by a density matrix? For example, you might have two atoms in your lab, system A and system B, and due to their prior history, again, the whole universe might be a pure state, but even the AB subsystem is not in a pure state. It's described by a density matrix. In that case, we want to find descriptions just for A or B. So let's remember the classical version, which we actually discussed in the last lecture before the break. I'll call the systems X and Y rather than A and B for classical systems. And the classical systems is that we are probability spaces. So we have a probability distribution rho of xi and yj, where xi are the states or the outcomes of x, and yi are the states of y. So rho is a joint probability distribution for two random variables, x and y. As we'll gradually come to appreciate, that's the classical analog of a density matrix, rho AB for the joint system A and B. In that case, classically, we exploited in the last lecture the fact that there are reduced probability distributions for systems X or Y. So rho of X, if you want a probability for the variable x of system capital X, you don't care about the value of y. You sum over all values of y for given x. And so, likewise, if you want a probability distribution classically for y, let's say yj, you sum over the value xi of the x variable. So classically, we use partial sums over what are possibly unobserved variables, or variables you want to. I'll put unobserved in parentheses because they might be variables you don't want to take into account, or variables you didn't observe, to get reduced probability distributions. So we want the quantum analog of that. I raced through it probably way too fast in one of the lectures before the break. The quantum analog is called a partial trace. A trace over the states of B. Well, in the classical case, we did a partial sum. If we want a probability distribution for x, we sum over y. So the quantum version is to take a trace over states of B to get a density matrix for system A. Or vice versa. You would take a trace over A to get rho B. unfortunately, it's a little bit messy to write down what a partial trace is. So I feel I have to write it once, but it's a little bit hard to write it. It's better to get the idea than to get lost in the formula, but it's very hard for me to, well, many of you are familiar with the concept of a partial trace, but if you're not, it's a little bit hard to help you be familiar with it without writing down the formula once, though it's unfortunately a bit messy to do so. So let these be bases of systems A and B. Then any rho AB will be, we'll just take the form, well, what will be? It'll be some ij, I prime, and j prime. I'll put I prime and j prime in the ket and I and j in the bra. And then we need some coefficients, which I'll call alpha ij, I prime, j prime. So what I've written is simply a completely general matrix on system AB. For it to be a density matrix, it's Hermitian and positive, but and trace 1. But as I've written it, it could be any completely general matrix. Now, if we have any operator, OAB, then its expectation value, by the definition of a density matrix, would be the trace of OAB times rho AB, the density matrix of system AB. And that's just telling us, okay, we could write the classical analog of that formula. See, an observable would be a function f of xy, and the expectation value of f would be the sum of f of xy times the probability distribution p of xy. That's the classical version of this formula. But now suppose that OAB only acts on system A. Well, before we do the quantum version, let's do the classical version. So if f of xy really only depends on x, then its expectation value is the sum over I and j of f of xi times p of xi and yj. But the only thing here that depends on y is the probability distribution, so we can do the sum over y, and that replaces, well, I called it rho over here. That replaces rho of xy by just rho of x. It classically, rho is a probability distribution, so you might want to call it p. So this is the operation that classically that we want to imitate quantum mechanically. So in the quantum version, OAB is some OA tensored with 1 on B. And now we're going to insert this operator in here. And we find that the trace of OAB times rho AB, well, it will be the sum over ij, I prime, and j prime of all these coefficients. Then we'll get two matrix elements. One is going to be a matrix element of OA between states I prime and I. And the other will be a matrix element of the identity of B between statements J and J prime, states J and J prime. But this is a Kronecker delta because we used orthonormal states we worked in an orthonormal basis. So the sum over 4 indices reduces to a sum over 3 indices, alpha ij, I prime j. Might be hard for you to tell, unfortunately, the difference between my primed and unprimed variables. And this can just be written as the trace of rho A times OA where we can read off from the calculation what rho A has to be. So, the trouble with what I've just explained is that I believe the audience is divided between those who are quite familiar with it and those who have trouble following it when it's written on the blackboard. But what we've learned is that we can get rho A by forgetting the B system and setting the initial and final state of the B system to be equal. In other words, we forget B and sum over the unobserved states of the B system.
I think in your notation, the Ra is I prime.
I wrote that here. Oh, I see, yes. Thank you. Right. In going from this formula with matrix elements to a formula with an operator, we move the bra past the ket, so the prime ends on the other side. Any other comments or questions? Now, this is usually written so you have to get used to this operation, which when written out in indices looks a little bit messy, but you can get used to it. It's usually written that rho A is the trace over B of rho AB. So that's the analog of the classical formula, which was that rho of x, let's say, was the sum over y of rho of xy, the way I wrote the classical formula. So summing over y is like taking a trace over the states of system B. Okay, any questions about that? Okay, so we're finished with our introduction to density matrices, and now we're going to move on and discuss entropies. So the basic definition of the von Neumann entropy von Neumann defined S of rho to be minus the trace of rho log rho. Now, he had both a predecessor and a follower, both quite distinguished, with very similar formulas. So first let's remember the predecessor. namely Gibbs, or maybe we should say Gibbs and Boltzmann, but Gibbs put it in the form I'm about to say. Gibbs considered atoms in a box, and he described the system by a probability distribution function for position and momentum of all the atoms in the box. Actually, this is a good reason not to have called the probability distribution P, because the momentum is also P. So to Gibbs, there was a probability distribution rho of x and P. And Gibbs' formula for the entropy was minus the phase space integral of rho log rho. Now, as we've stressed, the expectation value of any observable is the phase space integral of that observable times rho. So rho is the classical analog of the density matrix. And one interpretation of what von Neumann did is that he understood that the density matrix is the quantum analog of the probability distribution function, and the trace is the quantum analog of the integral over phase space. So this formula goes over to this one in the classical limit. Incidentally, this was not actually Boltzmann's formula for the entropy, I believe. So Boltzmann imagined that rho is constant. Well, Boltzmann said S is the logarithm of W, where W is the accessible volume of phase space. But in the thermodynamic limit, Boltzmann's formula is equivalent to Gibbs's. And the reason it is that so let curly B be the accessible part of phase space. And let the phase space density be constant in curly V and 0 outside. That means that rho is equal to 1 over the volume of curly V, which is Boltzmann's W, times a theta function with its support in the region V. And if you make this assumption about what the distribution function is, then you'll find that the Gibbs formula goes over to Boltzmann's. Now, of course, there was some idealization in making this assumption, but near the thermodynamic limit, this is a good enough approximation. In other words, as you go to the thermodynamic limit, the energy of a system is practically constant, or the fluctuations are negligible. Anyway, well, if you're studying the Gibbs formula at thermal equilibrium, the Boltzmann formula is a kind of microcanonical version. So whatever you know about the relation of the canonical and microcanonical ensembles in the thermodynamic limit is more or less an explanation of why the Gibbs and Boltzmann formulas are equivalent. Anyway, though, for us, we're interested in the Gibbs formula because it's the classical limit of the von Neumann formula. Both formulas are much more general than Boltzmann's. Boltzmann's assumption about the probability distribution function makes sense in some kind of equilibrium, but only there. It's ultimately very important in the applications we'll make to gravity that the von Neumann entropy is universally defined for any state. It has nothing to do with whether you're in thermal equilibrium. So anyway, Gibbs was one illustrious predecessor, or Gibbs and Boltzmann were illustrious predecessors of von Neumann, but there also was an illustrious successor, Shannon, whose work we discussed in the last lecture before the break. Shannon considered this random variable with probability p of xi to to find it in the ith state. And he defined the entropy to be minus the sum of pi log pi. So Shannon's application was completely different from what von Neumann envisaged. But you can think of Shannon's definition as a special case of von Neumann's definition, because if rho happens to be diagonal, then we can immediately calculate that S of rho is minus the sum of pi log pi. So, as I've told you, if a system has the density matrix rho, you can think of it as being in the ith state with probability pi, and that gives a classical probability distribution. There's much more in quantum mechanics than that classical probability distribution, because you might manipulate the quantum system by operators that are not diagonal on this basis. So forgetting rho and only remembering the probabilities will lose you a lot. But just to calculate the von Neumann entropy, all you need are these probabilities. And so the von Neumann entropy is the Shannon entropy of the corresponding probability distribution. So since that is the case, we know some properties of S. It's 0 if and only if the density matrix has rank 1. That means that 1p is 1 and the others are 0. The only way, since the p's are between 0 and 1, the only way to make minus p log p not be positive is to make it 0 if p is 0 or 1. So the only way to make the entropy 0 is to let rho be rank 1, in which case the entropy is 0. Otherwise, it's positive. And it has the maximum value log n, where n is the dimension of the Hilbert space that we're working on. The maximum occurs if rho is a multiple of the identity. One over n times the identity, in which case we say the system is maximally mixed. So S equals 0 means we didn't need density matrices, really. We could have described the system by a pure state psi. S positive means that rho has a higher rank and that means that the system, we usually describe it by saying that the system is entangled with something else. Well, maybe it's better to say that the system might be entangled with something else. That's a possible interpretation. If the system is entangled with something else, then it will have a density matrix of rank bigger than 1. Remember that entangled, sorry, I forgot to use the word entangled. Entangled simply means that there are multiple state terms in this decomposition so that system A isn't described by a pure state. When you study a system that has von Neumann entropy, you can always assume that the entropy came from entanglement with something else. Because, as I've explained near the beginning of the lecture, every density matrix has a purification. So, every row A comes from some psi AB, its purification. And then, then you would say that positive entropy means that psi AB is entangled. Entangled just means that it's not a tensor product state. Now, many classical facts about entropy have analogs for quantum entropy, but the proofs are often different, and in one important case, the proof is much more difficult. And there are some differences. But first, a nice fact. With no classical analog. If A and B are in a pure state, psi AB, then they have the same entropy. I'll usually abbreviate S of row A as SA and S of row B as SB, if it's clear what the density matrix is. So, you see, that's because the same Schmidt decomposition is used to construct either density matrix. Row A was the sum of pi times I, projector onto I of state A. Row B was the sum of the same coefficients times the projector onto state I of system B. Since the coefficients are the same, the entropies are the same. This is a nice and, as you'll see, very useful fact that has no classical analog because there's no classical notion of purifying a probability distribution. So quantum mechanically, you could always possible that a system is a subsystem of a larger system that's in a pure state. But classically, it never happens that you have a random variable, but if you included some other random variable, there would be definite outcomes. Definite outcomes would be the classical analog of a pure state. But classically, you can never add more random variables and get less randomness. Quantum mechanically, you can enlarge a system and get a pure state, which is the closest that quantum mechanics has to not having randomness. So this is a very nice classical fact that has no, sorry, a very nice quantum fact that has no classical analog. Gosh. Turns out if you explain these things on the blackboard, it takes a little bit longer than you think it's going to take. So the next thing I'd like to explain about, well, the first sort of non-trivial fact I want to explain about the von Neumann entropy is concavity. So let row 1 and row 2 be density matrices on the same Hilbert space H. Now, a density matrix is just a positive matrix of trace 1. So it follows that we can interpolate between them by a family of density matrices. A linear combination of density matrices with positive coefficients that add up to 1 is also a density matrix. So then we can define the von Neumann entropy of rho of t, and I claim that its second derivative is negative. Assuming that rho 1 is not equal to rho 2. If rho 1 equals rho 2, trivially, this derivative is 0. So the second derivative being negative means that if you plot s of rho of t as a function of t, it has whatever values it has at 0 and 1. And it's everywhere above that curve. So s of rho of t is bigger than t times s of rho plus 1 minus t s of rho 2 for all t between 0 and 1. We'll prove this in a second, but this is the corollary. And then by induction, or because it's true for concave functions, if rho is the sum of pi rho I, where the sum of the pi's is 1. In other words, here I've written rho as a linear combination of two density matrices with positive coefficients that add to 1. More generally, it could be the sum of any number of density matrices with positive coefficients that add to 1. Then induction applied to this inequality gives that s of rho bigger than the sum of pi s of rho I, assuming the rho I are not all equal. Of course, it's an equality if the rho I are all equal to rho. To get this formula from this one, well, here we split rho as a sum of two terms. But we could further split rho 2 as a sum of two terms, giving a three-term formula. We could keep doing it, and we'd eventually get this formula. So this one, which is extremely useful, is a corollary of this one, which we will prove in a moment by establishing that concavity. So what the formula says is that if you take a mixture of density matrices, that increases the entropy. Here's an example. The rho I could be pure state density matrices. Then all the right-hand side is 0. But if the rho I are different pure state density matrices, then the sum of pi rho I is not a pure state density matrix and will have a positive entropy. So if the rho I are pure state density matrices but are not all equal, the right-hand side is 0 and the left-hand side is positive. So that's an example of this formula. This formula has a lot of nice applications. Any questions before we give the proof of the second derivative being negative? So S was minus the trace of rho log rho. So first we'll calculate the first derivative of S. And I claim it's minus the trace of rho dot log rho. Well, why is that true? Well, you see, obviously if I differentiate S with respect to t, one term will involve rho dot. But you should worry that we should also differentiate the logarithm. Why is it that if we differentiate the logarithm, we don't get an additional contribution? Well, first I'm going to give a wrong argument. If rho and rho dot commute, then we'd say that minus trace rho d by dt of log rho would be minus trace rho inverse rho dot, which is minus the trace of rho dot. But that's 0 because the trace of rho is always 1. Now, that argument would have been correct classically because classical probability distributions commute. Quantum mechanically, it's wrong. Quantum mechanically, the right way to do it is longer. You write the formula log rho. We're going to use this formula in a second anyway. Log rho is the integral from 0 to infinity ds of 1 over s plus 1 minus 1 over s plus rho. So now this is a correct formula for matrices, and we don't have to worry about non-commutativity because only one matrix appears here. We can diagonalize it, and since we can, to check this formula, it's just a matter of checking that it's true for numbers. Since it's true for numbers, it's automatically true for positive Hermitian matrices. Therefore, we can differentiate well, you do need to know now that d by dt of 1 over s plus rho is minus 1 over s plus rho, rho dot 1 over s plus rho. That's a true fact without assuming that rho and rho dot commute. I think I'm going to let you try to convince yourself that it's true. So then d by dt of log rho is the integral, maybe with the minus sign. Oh, sorry, it becomes a plus sign. So then the trace of rho times d by dt log rho now, we can use the fact that the trace is cyclically symmetric to bring this 1 over s plus rho around and combine it with its friend. And now we do the integral over s, and the integral over s gives 1 over rho. So we end up getting 0 because trace of rho dot is 0. But we didn't make the fallacy of assuming that rho and rho dot commute. We just had to work a little bit harder, but we didn't make the fallacy. Any questions on that? Okay. So we got the first derivative of rho. Oh, sorry. Okay. Now, you see, now we'll calculate the second derivative. But you see, from this formula, you see immediately that rho double dot is 0. Rho was defined to be linear in t. So when we calculate d2 as dt squared, we don't differentiate the rho dot. We only differentiate the log rho. And luckily, except maybe I erased it, we just differentiated log rho with respect to t. Oh, here it is, okay. So we use this formula. Trace rho dot times this thing. Is there something that I can help with? Okay. I love answering questions. Okay. This is negative because it's the integral of the trace of b squared, where b is 1 over the square root of s plus rho, rho dot 1 over the square root of s plus rho. So b is a Hermitian matrix, so b squared is a positive matrix. Its trace is positive, and therefore this is negative. So any questions on that calculation? Yes?
So here, how can we let me cross rho to move this?
All that I did was to move this factor from the end to the beginning. And then I use the fact that 1 over s plus rho commutes with rho, because any functions of rho commute. So I moved it past this guy and wrote it as a square. Then we did the integral over s. Any other questions? Yes?
Can I just write this entropy as a sum over the eigenvalues of rho, like sum pi log pi, and then do everything without worrying about computation?
I think you could have done second order perturbation theory. So you need to know the eigenvalues of rho as a function of t. So you could calculate the eigenvalues of rho in second order perturbation theory. And that would be a way to do it. So from that point of view, you'd use the fact that rho double dot is 0. And you also would use the fact that the second order shift in the energy. Sorry, I'm not 100% sure what would happen. I invite you to try to do it by second order perturbation theory. So, okay, this is the correct answer for the second derivative, no matter how you want to find it. Rho dot is the same as rho 2 minus rho 1. And rho is this linear combination. So the formula you're trying to get is this one. Whether there's a better, quicker way to get this formula, I doubt, to be honest, but I don't know. Any other questions? I mean, there isn't going to be an essentially different formula from this one. And this formula can't really be simplified because rho and rho dot don't commute. But of course, this can be written in terms of matrix elements of rho dot between eigenvalues of rho. So what other way you want to do to get this formula, I don't know, but there would be other ways, I'm sure. Any other questions? So we proved this inequality. It's a strict inequality if the rho I are not all equal. So I'm going to give a couple examples of the use of this inequality. Well, I think I'm going to give 2 proofs of one example. So we'll start with any rho. So rho is just a Hermitian matrix. I won't positive in trace 1. I won't tell you anything about it. But then rho d will be the corresponding diagonal matrix. Rho d is just the diagonal part of rho in some basis. So if you throw away all the off-diagonal matrix elements of rho, you still have a positive Hermitian matrix of trace 1. So rho d is a density matrix. And now I'm going to do the same computation we did before, but with rho d and rho instead of rho 1 and rho 2. So I'll let rho of t be 1 minus t rho d plus t times rho, where t goes from 0 to 1. So rho of 0 is rho d, and rho of 1 is rho. And we're going to use the formula to compare s of rho to s of rho d. And we actually will see in a little while, but it might not be till Thursday at this point, that that's theoretically useful. So in this example, d by dt of s of rho of t, well, in general, it's minus the trace of rho dot log rho. But at t equals 0, in this particular case, d by dt of s of rho of t at t equals 0 is minus the trace of, rho dot. With this choice of rho dot is rho minus rho d. And then we have log of rho d. In other words, setting t equals 0, rho becomes rho d, and rho dot at any t is rho minus rho d. But you see, this is 0 because rho d is diagonal, so log rho d is diagonal. But rho d has the same diagonal matrix elements as rho, so rho minus rho d is 0 on the diagonal. So this is 0. So in this particular case, the first derivative is 0. We didn't have that in the general case. But we do have in general that the second derivative is negative. And combining those facts, we learned that S of rho is less than S of rho d, assuming they're not equal. If rho is not equal to rho d, then its entropy is less. So all I've done was I have a function whose first derivative is 0, and its second derivative is negative. So its value at 1 is less than its value at 0. So dropping the off-diagonal parts of a density matrix always increases the entropy. Here's an example. So here's a pure state. Then psi psi I'll take to be rho. For this particular example, rho would be this matrix, and therefore rho diagonal would be a multiple of the identity. So rho is a pure state, in this example, rho is a pure state density matrix. So in this example, S of rho is 0, but S of rho d in this example is log 2, because rho d is a multiple of the identity. Now I want to give another proof of the same fact because it's instructive, and unfortunately we'll have to end here today since we're running out of time. So next Thursday we'll have more on quantum entropy, and then we'll see if we manage on Thursday to discuss generalized measurements and quantum channels, or if that will spill to the following Tuesday. But I want to give another proof of the same facts because it's instructive. So suppose we're on an n-dimensional Hilbert space. There are 2 to the n diagonal matrices that I call U alpha, which are of the form plus or minus 1 on the diagonal for some choices of sign. Right? There are 2 to the n diagonal matrices whose diagonal elements are all 1 or minus 1. And they're unitaries. So let rho alpha be U alpha, rho, U alpha inverse. Well, rho alpha is a density matrix. Because what we've done is to conjugate a density matrix by a unitary transformation, and that preserves all the conditions. It's still Hermitian, positive, and of trace 1. Moreover, if we average the rho alphas over alpha, we get rho d. Because the diagonal part of rho commutes with all the U alphas, but the off-diagonal matrix elements have their sign flipped by half of the u's and not by the other half. So the diagonal density matrix is the average of the row alphas. So the inequality that S of rho is equal to or bigger than the sum of pi S of rho I if rho is the sum of pi rho I becomes S of rho d. So a strict inequality if the rows are not all equal becomes that S of rho d is bigger than 2 to the minus n times the sum over all alpha of S of rho alpha. But S of rho alpha equals S of rho for all alpha since they have the same eigenvalues. Rho alpha is unitarily equivalent to rho, and therefore it has the same eigenvalues, so all these terms are equal, and they're all equal to S of rho, and there are 2 to the n of them, so the right-hand side is S of rho. So that's another way to use the concavity inequality to show that making a density matrix diagonal can only increase its entropy. I'm going to stop here, but we'll just pause for a moment or two if there's questions on anything. Yeah.
How is rho alpha positive semi-definite?
How is what?
Rho alpha like positive semi-definite?
Rho alpha has the same eigenvalues as rho because it's unitarily equivalent to rho. So if rho is positive semi-definite, so is rho alpha. More specifically, it has the same eigenvalues. If one has positive eigenvalues, so does the other. They're equal, and therefore the entropies are equal. Any other questions? Okay, in that case, so on Thursday, we'll go on and we'll discuss relative things like mutual information, relative entropy, and so on, which you can indeed, if you want to be prepared, you can read my lecture notes, or you can read about it in Prescoll's article.